Town Projeto. This is a Groups 1 project. So here is a picture and a sketch of the real dumpster with dimensions with a length of 1 feet 7.25 inches, height of 3 feet 2.25 inches, and width of 1 feet 6.875 inches. And the most important features that we considered were the handle for carving, the two wheels for mobility, and the open close lid attached to the hinge.
To find the volume, you'll multiply the length, the width, the height, which gives us around approximate 8 feet cubed. The cost function optimization strategy. To minimize the construction cost of a dumpster with the same volume as the real container, we modeled the dumpster as a trapezoid box with slanted sides.
So in our design, we chose Trapezoid to do this project. So to find the volume, we have length times height times width bottom plus top width top and then divide two. So I chose length is 3 and then height is 2. So the volume is 8 feet cube. So to able to find the width and the width bottom and width top, so I gonna use volume divide length and height. So I got R approximate 1.33 something. So I let width bottom is 125 and then the width top is 1.42. Next slide, please. So this is our design. So we chose the design because we have the larger side on top so that we can easy to put all the trash in there, and beside that to minimize the price, so we use the big side because the lips, no matter how big or small, is to $50, so we choose the big side to do it. And then after that we use all the measurement to get our volume is about 8 feet cube. Thank you.
This is a table for the calculations for each component. On the far left columns, each component. On the second column are the dimensions for each part. The third column is the areas for each part. And then the next column are the rates. The last column is the cost, with a total cost of $68.48. Next, this is the starting of the optimization part. The equation on the top is the volume formula for our box. Which is length times height times width plus the width of the top divided by 2. And then the width of the top is proportional to the width of the bottom. So we can substitute that into the equation. And then the last equation on the bottom is with the width factored out. So it's length times height times width. 1 plus r over 2 equals 8. And this is our cost function. Cost equals C. The first term is for the base. The second term are for the sides, the front and the back. The third term is for the welding. And then the last term is for the lid.
In this case, we are going to continue with the functions that Oscar set up. So in this one, we're setting up the optimization function. So first, we have to find the Lagrangian function. In that one, how do we do is that subtracting the volume constraint function that is being multiplied with the Lagrange multiplier, and then subtracting that from the cost function that we find earlier. And then in here, the f function is going to be the volume constraint function is going to be set 0. so that we can make sure that the volume is going to be a cubic feet. And then we're also going to find the partial derivative of the cost function with respect to length and height, and also the width, the bottom width. Next slide, please. Can we go to the next slide? Next slide. Great. So in here, we're setting up the partial derivative of the Lagrangian to 0, and then make it equivalent to the partial derivative of the cost function, and then multiply with the Lagrange multipliers. So by using these, we can make sure that the volume constraint function is going to be 0, and then we're gonna get the dimensions of the minimum cost. In this table, we're setting up all of the dimensions that we find earlier, and then we find each of the costs for the plates, the floor, and then side, and then front and rear plates. For the lid, no matter what size it is going to be same cost. For the welding, since we have optimized dimensions, so the welding is also like costing less compared to the original price, and then our total cost is approximately $2 less than the original price.
Okay, I'm going to present the design conclusions part. And starting from the measurement, the dumpster is going to be 3 feet long, 2 feet high. The bottom width is 1.25 feet, and the top width is 1.42 feet. So we built optimized cost model using the given material and the welding process. So in order to keep the dumpster functional, we maintain the same volume of approximately 8 cubic feet and use the same trapezoidal cross section. Then using optimization techniques, we search for the dimensions that minimize the total construction cost. So our optimized design has a line equals to 2.38 feet. The height is going to be 1.39 feet. And the bottom width is 2.26 feet, and the top width is going to be 2.56 feet. The container has almost the exact same volume, but it's shorter and wider compared to the original one. And based on our cost calculation, the optimized design cost is going to be $66.82. So our improved design saved about 1.64 per dumpster, which is roughly 2.4% of the total cost. Refer to the recommendation if to make the optimization possible, we had to simplify the structure and the construction models. And if we were advising to a real company, we would definitely recommend our optimized model because it do reduce the cost. Even a $1 to $2 reduction per unit can make up a very big difference because we not only make the cost lower, but also make the dumpster more shorter and wider, and it's easier to load and more stable. To make a workable cost model and perform the optimization, we made several assumptions about the dumpster's structure and construction process. So these were necessary to allow mathematical analysis, but they also limit the accuracy of the real cost. Our main assumptions, like
This part is to continue the design conclusions. So in order to make our optimization model more thoughtful and efficient, we introduce several structure simplifications. First, our dumper step doesn't include any internal reinforcements or ribs. And second, we assume all panels are flat steel plates. We also assume the welding is minimal, only the shortest lines needed. For metals and fabrication, we assume the steel sheets can be cut perfectly with steel waste, so and there are no heating or bending is required. And okay, we also simplified the components. The list always costs $50, no matter the geometry, and we completely ignore small hardware like hinges, brackets, or wheels. And because of these assumptions, the cost from our model represents a theoretical minimum. In real-world production, reinforcement, fabrication waste, and complex assembly would be all increase the cost. So what we are really representing is not a final production-ready dumpster, but a baseline that shows the cost efficiency of the design.
After meeting several times and as a group, we ended up having the following reflections. So the first one is that modeling a simple trash bin showed that the assumptions and unit conversions are needed once you turn a real object into math and you do all the mathematical modeling. Also, doing the project too late didn't give us time for everyone to check everyone's work. Another thing is that setting up the cost function connected geometry with real costs, which made all the mathematical modeling more practical. We also saw how small algebra or calculator errors changed our best design. And so also using technology was very useful, and working as a group let us divide tasks very efficiently and finishing up faster. Well, thank you very much for listening.